Okay, hello everyone. Today we will be presenting our Niger River RoPax ferry concept design called the MVC Señor. So to get started with our outline, first we'll introduce our engineering team as well as our industry mentors. Then we will discuss technical, system, and regulatory requirements, followed by principal characteristics. We're going to move on and discuss our lines plan, vessel arrangement, as well as our structural arrangement. Then we'll go over weights and centers, hydrostatics, and stability data. And finally, we'll conclude with going over our mission-specific systems, as well as electrical and propulsive systems. So for our engineering team, it consists of Rebecca Ashmore, myself, Ben Calkins, Andrew Mullan, and Abigail Price. We would also like to thank our industry mentors for all their invaluable assistance with this project, including Satchel Douglas, Rob Kelly, Professor Michael Martin, Jeff Robert, Roy Serafian, Jeff Upmark, and Umberto Varbro. So to start with our technical requirements, we were tasked with designing a Niger River RoPax ferry to be operated in Nigeria. Specifically, we have to serve the three cities of Onitsha, Ida, and Ndoni. For some distances, Onitsha and Ida are separated by 113 kilometers of river, and Onitsha and Ndoni are separated by 77 kilometers of river. So we were given a little bit of leeway with how we carry out this task, and we've decided to have 2 ferries each day to start in Onitsha and proceed outwards, and 2 ferries start in the outwards towns and come towards the center. We need to have a passenger capacity of each ferry of 200 passengers, as well as a cargo capacity of 20 small freight vehicles. We are strictly limited to operating hours of 6 a.m. to 6 p.m. for safety reasons. And this dictates our minimum range. We have to have a ferry that can transit from Onitsha to Ida in that 12-hour period, dictating the range of 113 kilometers. Because of shallow sections in the river, we're restricted to a maximum draft of 1 meter, which is designated most of our design decisions throughout the engineering process. And bridges have limited us to 35.4 meters of air draft and 32.8 meters of beam. We are restricted to steel or aluminum for construction and must have a service life of 30 years. Now, for some system requirements, we have to use green technologies as much as possible. The Nigerian government prefers the use of compressed natural gas or electric power, so we've decided to opt with electric power, carried out with batteries. We must have strong maneuverability to be able to operate in the river current and reduce our noise and vibrations. We must design the electrical plant for our full operational load profiles expected, and we have to have sufficient water capabilities for both potable water and sewage and other water. Ventilation is required for this vessel. However, heating and air conditioning were not required. We've added it only for the battery room to keep them at a safe temperature. Anchoring and mooring is required as well. We must maintain a low wake and also add virtual aids to navigation among the bridge systems. The vessel must be designed to be able to operate in the riverine environment and keep itself protected from any hazards. For passenger facilities, we have to include seating. We've also opted to add facilities for dining and food because of the 12-hour length of the voyage. For crew facilities, we must have overnight accommodations just in case the crew has to stay on the vessel overnight. This includes provisions for the 2 security guards who will also be living aboard the vessel. And most importantly, we have to have a way to load the passengers and the cargo vehicles aboard the vessel safely. Now, for some regulatory requirements, they can be broken down into 3 main sections. Structures, machinery, and systems are designed according to Class NK's steel ships rules. Intact stability is in accordance with the IMO's rules for intact stability, as well as Class NK's rules for inland waterway vessels. Finally, life-saving appliances and firefighting is designed according to Title 46 of the Code of Federal Regulations. So to introduce our vessel, we have the following principal characteristics. Our length overall, including the fenders, is 72.8 meters. We have a length at the waterline of 60.6 meters. And in order to achieve buoyancy with a strict operating draft, we had to have a large beam at 22.8 meters, which 20 meters is at the waterline. Our fully loaded draft, according to the current weights and centers, comes in at 0.95 meters, meeting the strict operational limit, and we have a depth of 4.5 meters. Our current displacement clocks in at 978 metric tons, and we have an installed battery capacity of 8.9 megawatt hours to be able to carry out a full voyage over the longest length of the river. For propulsive power, we have 240 kilowatts installed to operate our paddle wheels, and we have a design speed of 6 knots that can be met with that propulsive power. Our passenger capacity is 200 as dictated by requirements. The vehicle capacity is 20, also dictated by requirements, and we have opted to design for a crew of 12. I will now pass on to Andrew Mullan, who will present on our lines plan.
Thank you, Ben. Before I get into the lines plan, I should discuss a little bit about what drove our decision in our hull form. Obviously, the shallow draft meant that we would need to have a lot of buoyancy inside the hull. Because of this, we figured we'd need to have a wide beam. Additionally, because of the owner's requirements of ease of construction and affordability, it was necessary to make this vessel as easy to construct as possible, especially given the remote location of the Niger River. For this reason, we have developed this lines plan. I will point out some key features. The first being flat of side for almost the entirety of the vessel. This flat of side eases construction and makes it much more cost effective to build. Additionally, we have a parallel mid-body from roughly stations 2 to 7, again, easing construction and making it more affordable to build. We also have flat at bottom in this section. Finally, we added an 18-inch constant bilge radius, again, to meet the regions of the side shell and bottom shell, which are both flat side and flat at bottom. And finally, we have the skeg. We have 2 skegs that have been developed, 8 meters from center line each, and they've been added to improve the directional stability of the vessel in accordance with our maneuvering requirement. These skegs terminate 1 meter forward of the transom and extend all the way to baseline for dry docking purposes. Now let's talk about the general arrangement for a little bit. The first thing to notice is the waterline of 0.95 meters on this inboard profile, as well as 1 meter, 4.5 meter, and 8 meter above baseline decks, the machinery deck, main deck, and A deck. Additionally, note the rake at the bow, while not improving the performance of the vessel, was necessary to increase the length of the vehicle lanes. During the design spiral, we found that by increasing the length of vehicle lanes, we could actually cut 1 lane out and decrease the beam from about 24 meters to 22. There's numerous stairwells throughout the vessel so that passengers and crew can easily navigate from the machinery deck, the main deck, and the A deck as necessary, as well as in emergencies. Finally, notice the machinery room located at midships. We will discuss this in further detail, but that is due to the side-mounted paddle wheels on port and starboard. For the machinery deck, the first thing to point out is the battery rooms. We're a fully electric vessel, and we split these battery rooms in 2. One of the main reasons for this decision was to allow a passageway to be developed in between so that the crew could make it through the vessel without having to walk through the battery room. Additionally, the batteries are run on separate battery management systems to a common bus, which allows for redundancy in case one goes offline. Finally, the battery rooms have been oversized so that if the battery footprint were to expand, more batteries could be installed in the vessel without harming the space requirement. Propulsion motor rooms are located adjacent to the paddle wheels to minimize the length of shafting required to power these paddle wheels and support any other equipment necessary. And finally, the paddle wheels located at midships, port and starboard, have been sized to power the vessel at 6 knots. For the main deck, the first and most important thing is the passenger accommodations. After all, this is a passenger and vehicle ferry. Passengers must be comfortable for the 12-hour journey. You will notice that there are 200 seats plus bench seating for any disabled passengers, meeting the requirement that each passenger have their own seat and not need to stand during the journey. Additionally, above the seats, there are luggage racks similar to on an airplane, allowing passengers who do not arrive in vehicles to stow their luggage above them. You'll notice on the starboard side aft, a galley, a bar/food service, and a passenger mess. This is how any food and drink operations will be conducted. Food stores located within the galley. Again, on the port side, further aft, we have adequate restrooms, women's, men's, and handicapped to accommodate the passengers on their 12-hour journey. Finally, you'll notice the vehicle lanes on centerline, as discussed earlier, extending far forward and aft, and 2 areas have been designated as vehicle ramp landing zones. These vehicle ramps are installed shoreside when we discuss later, but adequate room has been left to ensure that vehicles can load onto the vessel without interfering with the ramp. Finally, the A deck. A typical crew stateroom consists of a bunk, a desk, and a personal bathroom. Additionally, the crew lounge and mess are located on the A deck separate from passenger spaces. This was especially important because the crew may be expected to stay overnight and need their own space to recreate and eat. We have an EDG room, a marine evacuation slide, and davit launched fast rescue boats, all contributing to the safety requirements of our vessel. Passenger gangway will be loaded onto the A deck so that passenger and vehicle loading operations do not interfere with each other. The passengers who load on the passenger gangway can then proceed down the stairwell to the main deck and into the accommodations area. Finally, you'll notice the bridge wings extending port and starboard as far as possible to ensure adequate visibility when maneuvering. The windows of the bridge have been angled in accordance with Class NK rules for visibility of bridges. Finally, the structural arrangement. This vessel is a longitudinally framed ship with longitudinal spaced roughly 700 millimeters apart. The reason for the longitudinal framing was driven by the fact that this is a passenger ship. While Class NK does not mandate that passenger ships be longitudinally framed, they do say that they should have a double bottom. This double bottom must be longitudinally framed. Benefits of longitudinal framing include more members contributing to the longitudinal strength of the vessel, increasing the section modulus. Additionally, it makes the vessel less prone to buckling, which is not a concern, but it's still there and contributing. Some of the dimensions include, as mentioned, the 700 millimeter spacing longitudinals, 3,500 millimeter spacing of floors, and then 4,200 millimeter spacing of frames. Finally, the material chosen for this vessel was ASTM A36 mild steel. You may be wondering if we were weight limited and draft limited, why we chose steel. Although we were weight limited, another owner's requirement was ease of construction and affordability. In remote regions such as the Niger River, there are not many shipyards nearby, nor are there specialized aluminum welders as there may be in other areas of the world. Because of this, it would be more expensive to construct the vessel out of aluminum rather than steel. Additionally, steel is a more common structural material, so there's more rules developed around it. It's cheaper, it's more rigid, so it provides a more robust protection in the riverine environment, and it is less prone to thermal transfer in case of a fire when compared to aluminum. I'll now pass the presentation over to Beck to discuss weights and centers and hydrostatics.
Thank you, Andrew. Given the draft requirements for our vessel, the weights and centers are rather important. A significant weight of the vessel is structural. However, even with the steel structure, the total displacement is 978 metric tons, and our draft requirement is met at 0.95 meters. The lightship section was broken into the sections of steel, electric, machinery, outfitting, and auxiliary. These were primarily scaled using Strobiner's ratio metric method. The deadweight total included potable watering using the industry standard, assuming people is 185 pounds, vehicles is 4.5 tons, and food stores is 10 pounds per person. At the full load departure state, the potable and cooling water are at 98%, the gray water at 10%, and food stores at their full weight. At the full load arrival state, the gray and cooling water are at 98%, while the potable water and food stores are at 10%. The table of hydrostatics shows the various displacements in metric tons and drafts at the three conditions, all of which meet the maximum draft requirement. For the trim in the loaded condition, the vessel is essentially at even keel. Typically, the keel is aft for ocean-going vessels. However, due to the slow speed and barge-like hull form, the effect of the even keel is negligible. The impact stability criteria were applied to the vessel in the lightship, full load departure, and full load arrival full load conditions. All 8 criteria were met in all 3 conditions. The criteria concerning absolute angle and maximum righting arm is met through the accommodation included in the Class NK rules for wide beam and shallow draft vessels. The last residual area criteria was additionally met in order to meet the 5th criteria of the absolute angle of the maximum righting angle. This ensures enough energy early on in the GZ curve. The first 2 damage stability criteria are beyond the conceptual design scope, although they are included, and then they included to be aware of future requirements that would be needed to be met. The floatable length criteria is analyzed for this vessel and are the primary means of analyzing damage stability here. Using a simplified model, the 2-compartment flooding standard was additionally increased to 4 components to ensure meeting the criteria. The TPUs don't exceed the margin lines, even in the 4-component analysis, which demonstrates a primary means of meeting the damage stability criteria. I will now pass it on to Abigail, who will talk about our vessel systems.
Thank you, Beth. I will now be discussing the various systems aboard our vessel, beginning with propulsive system. Due to the vessel's shallow draft, a rather unique form of propulsion was determined to be necessary. In our case, paddle wheels. Our vessel has 2 side-mounted fixed paddle wheels that are turned by 2 200 horsepower motors, 3-phase induction motors. Paddle wheels are chosen for their efficiency at shallow drafts and slower speeds. Thruster units were considered. However, the propeller diameter would be very limited and therefore too many would be needed to be practical. An articulating paddle wheel design, as opposed to the fixed paddle design ultimately chosen, was considered. However, it was concluded that it'd be too complex to maintain. As shown in the rendering, the buckets are staggered. That will lessen noise and vibration and also induce more continuous thrust as the wheel rotates. To size our paddle wheel, a design speed of 8 knots as opposed to the ship design speed of 6 knots was used to account for the river current when the vessel travels upriver. The buckets themselves are wooden because of their affordability and ease of maintenance. These paddles can also be replaced easily at port as necessary. I'll now discuss our electrical system. The MVC Señor is a fully electric ferry that operates using lithium-ion batteries. While multiple battery systems were considered, Corvus Energy's Dolphin series was selected due to their high energy density, limiting weight aboard our vessel. The electrical loads were estimated using propulsive power and hotel loads of similar vessels. To preserve the lifespan of the batteries, excess energy was installed on board to ensure that the batteries drained a maximum of 80% during standard operations. During the 12 hours when the vessel is not in operation, there is a shore power connection that charges the battery so that they are fully charged the next morning for the vessel to be in operation again. The battery room, as mentioned before, is sized to be much larger than the battery footprint of 15 meters squared to ensure that there is room for maintenance and for future growth of the vessel. Corvus Energy has a battery management system that we will be using that will distribute power to electrical loads of our systems, including steps of 480 volts, 240 volts, and 120 volts. Finally, I will discuss our mission-specific systems. As the MVC Señor is a RoPax ferry, its mission is to transport passengers, vehicles, and their cargo to the cities of Anishta, Ida, and Adoni. Therefore, our mission-specific systems revolve around these parameters, first of which is our vehicle loading and unloading. Vehicles will be loaded via a shoreside ramp at the stern of the vessel and be unloaded in the same manner at the bow. And when reaching the second port, will be loaded via the bow and then exit via the stern. The passengers not in vehicles will be allowed to board our vessel at the sides using the passenger gangways. They will then proceed down the stairwells to the passenger accommodation area. As mentioned previously in the GA section of this presentation, passenger accommodation includes seating, luggage racks, washroom facilities, and a bar area to purchase food and refreshments for the length of the journey. For our 10 crew and 2 security guards expected to stay overnight on the vessel, the A deck is used as a crew accommodations deck. This includes a mess hall, lounge area, laundry facilities, and sleeping quarters. To conclude, the MVC Señor is a fully electric vessel that operates in the Niger River to transfer passengers, vehicles, and their cargo to the cities of Anishta, Ida, and Adoni. I now welcome my group members up to the podium to answer any questions. Thank you for listening.
Yes, first of all, great job. I just wanted to compliment you guys. I think it's the coolest thing in the world that you're doing a paddle wheel. Like a modern day paddle. Okay, that's awesome. So I didn't know if that was a part of the requirements for the owner or not, and how you kind of came about selecting that. I mean, obviously, it's a big draft, but I mean, I didn't see that coming.
Frankly, neither did we. We considered many other propulsion options. It seems like every week as we were making the vessel that we had a different propulsion solution. However, it was suggested by our mentors and by some of our professors that in the case of our slow speed, that a paddle wheel would be most efficient. And while we first laughed it off a little bit, we eventually came around to the idea, and now we're very excited to have them on board our vessel. Yes.
Did you ever think of a hybrid on this? You said you could use gas or electric, or how about a combination?
Andrew, would you like to come up and talk about?
So the question was, did we consider a hybrid solution for this vessel? Initially, yes, but one of the owner's requirements was to keep it simple. They ease of affordability, ease of construction, ease of maintenance. Hybrid systems, we thought would get a little clunky and it was better to pick either one or the other rather than have to maintain both. Additionally, since we saw the vessel going fully electric anyway towards the end of its service life, we figured we should start out fully electric. Yes.
So in coming up with your general arrangement for both your passengers and your crew, are there any reason to consider local style, local norms, in those arrangements?
So the question was, in coming up with a general arrangement for our passengers and crew, was there any reason to consider local cultural norms? To be honest with you, we didn't really consider the cultural norms. Most of the general arrangement was based off of typical passenger ferries that we had experience with. Most of those ferries are based in the US. So there are different societal norms. In consultation with the customer in the future, it's possible that they would come to us and say that it wouldn't work. In that case, we would probably revisit that. But at this time, we did not consider that.
Thank you.
Yeah.
What are the block coefficients on your hull?
So the question was, what was the block coefficient? We haven't recalculated recently, but it was upwards of 0.85 at one point, which is pretty much a box.
I didn't see very much about how you get cargo on, I mean, it's a double ender. But what about the shore side? Are you expecting there to be ramps in place at these ports that you know, have some kind of onboard ramp that will get cargo off if there is not shore side ramp?
You guys want me to listen to? Yeah.
So the question was, are we expecting to have shoreside ramps and other cargo facilities available at port? So based on owner's requirements, there will be port facilities based on the design of this vessel. And we are also, the cargo itself is within the vehicles. So we're only transporting the vehicles on board the deck, and the cargo is secured on the vehicles themselves. So we're not expecting any additional cargo.
I would add to that as part of the owner's requirements, they mentioned that they were dredging the river. So, I mean, that could change the draft requirement a little bit, but in addition to dredging the river, they, I think as Abigail said, they are developing an entire infrastructure to support this ferry. So we have a little more leeway to say that as part of the cost of the ferry, to minimize maintenance on board the vessel, we could increase the maintenance off the vessel, which is probably easier to do anyway.
Yeah, I think it's a great job as the conceptual design of a boat. I was just a little bit curious about the overall transportation analysis. There you mentioned 12-hour total end-to-end trip time. It sounds like there's going to be a total of 4 boats, and so it might not affect your concept design, but I'm just curious, was there any more work done in kind of the overall holistic transportation analysis on, the timing of boats and, where they're going to dock and that sort of thing. And then just one other question was also related to loading of passengers. I know you mentioned that there's space for disabled folks, but when you were talking about passenger loading, I think I heard you say that they can get it downstairs. Those questions.
Want to take this one?
Yeah. Okay, so the first question was a holistic transportation analysis done on the river? So we did a lot of analysis initially with how the route was going to work, because we were allowed as part of the engineering process to determine what kind of fleet was going to be made. So we looked at trying to do round trips, starting in Onitsha at the center and then going out to the outlying towns and coming back. But just based on the length, this would have required a speed that was not necessarily achievable with the draft that we had to meet, and also the strict capacities. So we did try to design for this, but it didn't really work out. So then we decided to have a vessel that would just complete one leg of the journey each day, requiring at least 4 vessels to be deployed. So we did look at a couple different options for how to carry this out, but it was basically figured out that the most efficient way to carry this out and still meet the draft requirement required just doing one leg of the journey each day.
I can take a second. Okay, the second question was about the disability seating that we had, but the fact that the passenger loading was on the upper deck. I'll be honest with you, I wasn't really considering that in the design. However, what I imagine could be done, similar to some other place when we're trying to load disabled people, is that you could load them before the vehicles via the vehicle ramp, since it's a very wide space and it has a ramp. You could get them situated and then begin the vehicle loading process. That's not really something we've actually dove into. It's more just, that's something I can think of off the top of my head. That may be a way to deal with that. More questions? Yes.
I was interested in that wheel. It's interesting. When I've had projects like this, like, did you look at the speed of the paddle wheel and the speed of the motors? Those are often very different in the production.
Okay, I'm gonna hand that one to Abigail.
So the question was referring to the speed of our paddle wheel versus the speed of the motors. A custom gearbox will definitely need to be purchased and used, as motors generally do not run at 10 RPM. So we will need to, that's something that we haven't quite figured out yet, but we're working on figuring out how to achieve that. Yes.
Sort of follow on to the question that's still receiving. What was the rationale for having a separate access method for passengers as opposed to vehicles? I know there are some road tax ferries where passengers get on and just walk on the vehicle ramp. And what was the reason for making a separate entrance?
So the question was, what was the rationale for having separate loading for the passengers and the vehicles? Because yes, with the current arrangement, you could load them at the same time. So we've gone through a number of iterations on this vessel, changed every week. And one of the first designs had the passenger accommodations on center line and the vehicles port and starboard. With that arrangement, with the vehicles having to turn and navigate around, we figured it was better to load the passengers on the second deck to avoid getting in the way. With the new update, it is possible, yes, that the passengers could also load without interfering with operations, since the vehicles are on center line. However, we decided there wasn't necessarily a bad reason not to load them on the upper deck, so we kept that in the design.
I was a little surprised at the performance, 250 kilowatt motors. You talk more about the electrical load balance and thinking about fault fouling, aging, and the other electrical consumers on board.
Okay, so the question was, the propulsive load for the paddle wheels is a bit surprising at just a couple hundred kilowatts. So what kind of considerations were made there? So estimating the propulsive power required for a vessel turned out to be quite difficult, because there aren't really any series in NavCAD that can predict for this sort of hull form. We ran a bunch of different predictions and we got anywhere ranging from a few hundred kilowatts to several megawatts. So we had to turn to other ways to estimate the propulsive power. Basically, the way we ended up doing it was estimating as if the vessel was a barge, because our hull form is rather simple. So it's not that far off to assume that it's a barge. So we used a paper from Transport Canada to determine the power as a barge, and then proceeded from there. And we confirmed that that same paper also has results for vessels that they measured experimentally. And the propulsive power we have does align with their experimental data as well. So we are somewhat confident in this propulsive power estimate, but if you were to proceed with a more advanced design, it would probably be worthwhile to invest in model testing. For further electrical questions, I'm going to ask Beck to continue explanation.
Yeah. Actually, okay, I'm just trying to figure out, would that just change the one line of EPLA? Yeah, okay. Sorry. I'm hoping this is actually in here for an analysis. Do we have that one?
No,
Oh, no, we don't. Okay, my mistake. So for our EPLA, which was brought up on the previous team, our electrical plant load analysis, we then was able to scale that in terms of referencing with, we used a variety of different types of machinery references. I believe for this motor specifically, it was from was it our total plan that was carried through?
Our motor was sized.
Yeah, we sized the motor based on the propulsive load, and then from that took those specs and just put in our RPL in.
Yes,
I'm not sure if that was the question, but
yes, sorry. Any more questions?
A few online. Any other questions in here first? Just going back to the decision to go with paddle wheels, seeing that they're on the side of the hull, are you concerned about floating in the river? Or, I'm not sure what the conditions of that river is, a river that floods often and has high currents, or what would be able to.
So the question was, do we have any concern using side mounted paddle wheels in terms of the river environment and things in the river? Yes, this was a major concern. However, when discussing different propulsion methods, it was going to be concerned with all propulsion methods. And the way we combat this is that each bucket is going to be, is rather inexpensive and can be easily replaced as necessary. And we have extended the, at least for in port, we have extended the fenders to protect the paddle wheels while in port. However, based on the other parameters, we decided this was the best way to avoid that issue. Any other questions?
Okay, so the online questions, first question was, could you address the frame spacing you chose and why you ended up, how you selected that frame spacing?
Okay, so the question was how we determined our frame spacing. So we followed the rules according to Class NK and designed as, we followed Part CS, which is for vessels under 90 meters. And additionally, we made sure to meet the requirements for passenger vessels. So we opted to go with longitudinally framed, a longitudinally framed vessel because Class NK requires double bottoms for passenger vessels unless you file with them to get an exception. So this dictated our max longitudinal frame spacing of 700 millimeters. And then the benefit of this is we do get to take out a lot of our transverse framing. So based on the rules prescribed in Part CS, we were able to have the floors and beams at just every 3.5 meters, and the transverse beams along the side are girders that can be every 4.2 meters. But basically, it all goes back to the Class NK Part CS and designing for a passenger vessel under 90 meters.
Okay, next question deals with the paddle wheels, or a couple of questions about paddle wheels. I'm going to try and combine them. Did you consider more than one pair of paddle wheels on the vessel, and at the same time, did you consider increasing the diameters?
The question was, did we consider increasing the diameter of the paddle wheels, and could you repeat the first part of that question, sorry?
First one, did you consider more than one pair, or one pair after?
Did we consider more than one pair? We did consider more than one pair very briefly. However, it was concluded that it would be a little too complex for our vessel. And in terms of increasing the diameter of the propeller and of the paddle wheel, it was based on the calculations to size it, and also increasing the diameter of the paddle wheel would increase it farther than our main deck, which we were trying to extend to protect them. So that was the reason why we sized it the way we did.
And then there's actually one more question about the paddle wheel, sorry. Can they be operated independently, decoupled or starboard?
Yes, they're actually on two different shafts with two different motors. So they, in order to have the increased movability, which is the benefit of side mounted paddle wheels, they are both independently operated.
And one more question I have on here regarding your skegs. Were directional stability calculations prepared for the skegs, or are these more conceptual?
Okay.
I'll take the question. So the question was for the skegs, did we do any real calculations that were they conceptual? The answer, no, we did not do calculations on the skegs. That was beyond the scope. I haven't learned how to do directional stability calculation, to be quite honest. The skeg development came from consultation with our mentors, who said that barges often have issues with directional stability. So the way it was formed was basically looking at various barges, seeing how they arrange their skegs, and most of them extended either fully to the transom or just short of it. And to baseline was specifically done, as I said, for dry docking to make sure that the boat actually sat on like the skeg and the flatted bottom to make sure there wasn't any uneven load. With regards to the stopping the skeg 1 meter short of the transom. The reason that decision was made was so that the length of water line would not be affected. In the loaded condition, the way the skeg is that because of the sharp transom meeting the bottom shell, there's very little I guess the best way to by cutting the skeg off 1 meter for the transom, you still have immersed bottom shell past the skeg, meaning like water line didn't change and none of the other calculations had to change. Any more questions? John?
You guys consider adding?
The question was, do we consider adding rudders for increased maneuverability? Not really. In the process of design, we started with twin shafts was first recommended. We went away from that due to, again, propeller sizing concerns. Then we looked at azimuth and thrusters, which would not need rudders. And again, those are too big. And once we came to paddle wheels, the fact that you could put one in forward and one in reverse, if you needed to, kind of acts the need, in our opinion, for a rudder in addition. Any more questions?
Okay, thank you very much.
Thank you.